Hey everybody, we're going to do a quick video on the theory and background, maybe is the right word for it, of the absolute zero lab 1 experiment. I am coming to you from orbit. That's pretty cool. Not a lot of air up here, so I will have to make this brief. Okay, let me share my screen here so that you can see some of the calculations that we will do. Okay. Alrighty, hopefully that is coming through just fine. So, what we've got here, lab one, this is going to be the absolute zero lab. Actually, it's the absolute zero and gas constant lab. So, what we're going to do is basically try to take a couple of different data points such that we know what the pressure is at a particular temperature, and we're going to use those 2 points to try we're going to use those two coordinates and a couple of data points to try and extrapolate backwards and find where the line that is the best fit line intersects the temperature axis. So the idea here is that um, with the ideal gas model, um, right, we have this, and we use the temperature in kelvins where the pressure is in pascals and the volume is in cubic meters. But what if we wanted to change because we know that the Kelvin temperature is the same thing as the centigrade temperature plus 273. So, given that, if we kind of take that and put it in here, what will happen is we'll find that it's NR times TC plus 273. Now, if I factor the NR through and I divide the V on the underneath, what I then end up with is I end up with an N divided by V times R centigrade temperature, right? And I'm going to put that all through onto the next part, which is added to N over V times R and 273, like so. Alrighty. Now that's what P is equal to. Note that this now looks like, if you consider the temperature in centigrade and the pressure to be independent variables, then what we're going to consider this to be is the same thing as y equal to m times x. Well, that should be like so, plus b. Okay. Alrighty. So this gives us a line, the graph of which, if I just kind of move this over, see if I can shrink this down a little bit, move it over. What would happen is if I'm going to graph pressure as a function of temperature, like this, right? Temperature, this would be the temperature in centigrades. This would be the pressure, okay? What we're going to do, I alluded to this slightly in the other video. We're going to take three different data points, okay? Unfortunately, they are going to be very closely spaced. So if I consider 100 centigrade to be here, say, and 0 is here. Oh, that's a bit far. Let's not do that. Let's do 100 to be about, say, here. So maybe that would be if I go 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So that would be 200 centigrade right about there. Let's get rid of this. Whoa, not that. Okay. Anyways, well, 200 is maybe about here. on this plot. So all our data points are going to be kind of like in here. We're going to get one that's going to be kind of close here. We're going to get one that's maybe about 50, maybe about halfway. So right about there. We might get one that's a bit closer on this side. Maybe we'll get another one right in between. So you can see that because of the closeness of the data, we have a lot of uncertainty. So your values will be fairly rough, okay? Nonetheless, what I want to do is get the pressure at the different temperatures and plot those. And you can do that in Google Sheets and then have it give you a line. Now, if you want Google to give you the line, that's fine. You go ahead and do that. I'm just going to freehand one in here like so. What we're looking for here is basically this temperature. Okay, that's the temperature that we're looking for. The best fit line will have your three data points and it will intersect the t-axis, and that is our best guess as to what the absolute zero temperature is going to be. If you want to draw this line on your lab reports, I am absolutely fine with that. I actually almost encourage that because of the second part of this, which I might just go through right now because it seems to make sense. What I want to look at, if you look at these three data points, you'll see they're fairly scattered, right? I haven't drawn them so much that they lie along the line. And I would say this is not the best fit line, but let's pretend that it is for a minute. What I want to do to find the uncertainty is to try and draw the two worst fit lines. Okay, this is the best fit line. What are the worst fit lines? The worst fit lines are ones that still take into account the data and try to model the data, but is not as good as the best fit line. So think about the worst fit line. What would be the worst fit line maybe on the high side? What would be the one with the highest slope? Maybe one that goes, let's just change color here. The one that goes possibly through about here. No, that's pretty bad. Let's try one that goes through about here. Well, it looks a little bit better. Okay, and it really is this type of process, eyeballing the worst fit line. So this is the one with the higher slope. What could I do on the lower end and find the worst fit slope on the smaller end? One that fits, I'll do this one in, say, blue here, maybe through about here or so. I'm trying to think about, yep, so I'm going to go, oh, nope, missed it. Let's try again. Well, close enough for government work, perhaps. And my freehanding. I am not doing this with a straight edge. But the idea is that you're looking to still try and model the data, but how bad could it be and still make you convinced that, yeah, that's an okay fit. It's not good, but it's okay. These would be your two outside ranges, right? So in other words, I wouldn't expect the slope to be any higher than the red one or lower than the blue one. And I wouldn't expect the absolute zero to be any higher than here or lower than, it's not going to appear on here, but let's just say it's right over here, right there. So I have a range for my absolute zero. For example, I could say my guess is this plus or minus about approximately what that range is divided by 2. And the same thing with the slope. The slope is related to the gas constant. So I'll get a value for the gas constant from my best fit line, and I'll get one from my two worst fit lines. So I'll get a plus minus value. Okay. That's how I want you to calculate or estimate the uncertainty in your calculation here. Okay. Now, uh, in order to do this, we have to take data. So the pressure we need and the temperature we need. So in the other video, I show you the experimental setup, but this is kind of what it looks like. Okay, like this. So I have a constant volume gas thermometer in which perhaps the water level, say, is here. All right, so this is water, and I'm at atmospheric pressure right now. So let's just say the water level is that much. Now, if you remember, if you have seen the other video, or if you haven't, what I did was I hung a tape measure right next to it, and I would say, all right, what's that reading? The reading on that tape measure, say 70 centimeters, is atmospheric. Now I'm going to take everything with respect to that temperature. Sorry, to that with respect to that measurement, so that if I then dip the canister into a cup of, say, warmer water, what's going to happen then is the temperature of the gas is going to increase, which is going to cause the gas to expand, and it's going to get larger and push the water more. It's right more like this. And this is gonna, oh dear, I can't erase that, can I? Oh dear. Oops. It's not so good. Let's put that back. Oh, I can't even touch that without erasing it. Oh, what a bummer. Maybe zoom in a little bit on it. Maybe I can just get this. Okay, good. So let's just say that the water got pushed back to a level here and went up to a level there. So now the level of the water is up here. And I would say this much height of the water is how high above. Actually, no. Sorry. I take that back. Just a minute. We're not done. The gas has expanded. I didn't finish my sentence. The gas has expanded and pushed the water, but what we need to do is return the water to this level right over here. What that means is I have to raise the left side of the tubing, and the water is going to push back against the air. So now I re-raise the water so that it does come back to here. And that means that as I push, as I go upwards with this, right? Let's say take that away. Okay. So as I go upwards with this, now the water level is perhaps up here. And that height is the height above atmospheric pressure that the water is having to exert in order to counterbalance the pressure from the air. So say that's a delta Y right there. And the extra pressure from the water is equal to rho g times delta Y. That's the pressure above atmospheric. So in order to find the total pressure, you have to add the atmospheric pressure to that. Okay. I have to add that, and that is going off the top of my memory here, but I believe it's this. If you need that many significant digits, which you don't, I would think. Nonetheless, you'll have now a pressure with which you can say, I have a pressure, right, that I've calculated. I have a temperature of the water. This is warm water. Maybe the temperature was equal to 55 centigrade. Okay, so I have a 55 centigrade water. I have a pressure, and that is a point on my PV graph. Maybe it's, say, this one right here. Uh, Hey, okay, maybe it's that one right there. Now I'm going to use ice-ish water. So it's going to go down to about 12 to 15 centigrade. Okay. The air is going to contract. The water level is going to come down. You're going to adjust the left side of the tubing so that the water level is still a constant right there. And then you're going to measure, okay, where's the water? Is it above or below? It should be below because you will have contracted the water. It's probably below the 70 centimeter mark, so maybe it's down here or something, and you're going to measure this little delta Y and you're going to say, it's P atmospheric minus that, okay? And you're going to calculate what the pressure is, and you're going to say, I have another pressure and I have another temperature. And I'm gonna get one, two, and three of those. Okay. Those are going to be your three values. Approximately room temperature, below room temperature, like colder water, warmer water, and those are going to be these three values right here. Okay. And from that, you're going to extrapolate a best fit line in order to find your absolute zero temperature. Okay. So in order to find the and before I go on to the next one, and you have the uncertainty because you can then, once you have those 3 points, you can then do your two worst fit lines and Google Sheets will not do this. You will have to do that part by hand. Two worst fit lines. You'll have your range of approximately where the absolute zero temperature should lie. Okay. Um, Note, this is a fairly rough experiment. It's pretty simple. Um, we're not going to get great numbers. Okay. You might get large uncertainties. Okay, that's fine. Just please be scientific about what you have found. All right. In other words, report what your values are. Make your best estimates. Don't estimate in order to get better numbers. Okay. Estimate to be transparent with how uh, how your data is fit. Okay. Everything comes down to how you analyze the data, and you just have to be truthful to it. Um, Second part of this is to find the slope of the line. So we're going to concentrate here on the best fit slope. Oh, wait, before I do that, I also want you to take your, so what I said in the lab was to uh, take your, um, equation given to you by Google Sheets and see if you can set x equal to zero. I'm sorry, set y equal to zero and solve for x in order to find the best fit lines x-intercept. All right, that's another way to see what the absolute zero temperature looks like. Okay. From Google Sheets, if you have it give you the equation, you can also do that. Set y equal to zero and solve for x. I want to go back to now, how do you find the gas constant? Okay, well, you can see here it's related to the slope. All right, right there, we're going to have the slope. What we need to do then is measure or have Google Sheets give us the slope of the line. The slope is n divided by v, and it's multiplied by r. So what we want to do then is, of course, to find r, we want to take the slope of the line and divide by n over v. All right. We need to find n over v. How do we do that? Well, go to the weather uh, page where for your whereabouts. Okay, so for example, I could go to Aptos or Watsonville or Capitola or SoCal or whatever, and see if you can look up what is the pressure, what's your local pressure, okay, and what's your local temperature. You can use those two values in the ideal gas model here. So you'll have a pressure, and it'll be divided by, and you'll take your local pressure and your local temperature, and this will give you your N over V for your local. All right, and that's what's going to go into right there. Um, Now you may see that and say, well, isn't that a bit circular? Yeah, it is a little bit, but it's what we have and it's what we'll go with. So, um, take a look at your weather, maybe whatever weather information you can get, either off your phone or off the internet or whatever you can find. What's the local pressure? Now, the local pressure is not going to be given in pascals or kilopascals. I can pretty much guarantee you that. It's going to be given in something like millimeters or inches of mercury. Okay. So, uh, in inches of mercury, 30 inches of mercury, if I remember correctly, is atmospheric pressure. Oops, one is one atmosphere, 30 inches of mercury. Um, that corresponds to 760 millimeters, and uh, you can convert from there. Alrighty. So that would be how you can find the two of those things. What I'd like for you to do is if you do use Google Sheets, go ahead and include a link in Google Sheets into your lab. It doesn't have to be very formal. It just should be something that is readable, describes what you did and how you interpreted the results and why. All right, so that is basically the lab for this week. And those lab reports, please turn them into Canvas by Tuesday, and that is, I think, the 11th. All right. So turn them in on Tuesday the 11th, and we will uh, go on to lab two this time next week. All righty. Hopefully that mostly takes care of your questions. This video, along with the other video where I go through the experimental setup, should basically help with taking the data and then analyzing it. So good luck, and I wish you happy weekend. Enjoy some constant volume gas thermometering. Take care, and until next time, folks.